Hi folks, how are you doing? Mr. Godber here, as most of you know, but I know some of you won't have met me before. I'm sorry to burst in like this to you in the middle of your longest summer holiday ever. I hope you're all enjoying your great holiday and you continue to do so. And I'm looking forward to seeing you all in September when we embark on the great journey that is A-level maths together. When we do that, it would be really great if we could hit the ground running so that we can start hitting some new content of what is A-level maths and not spend the first couple of weeks having to go over stuff that you were taught in GCSE, but which is quite sort of higher level there, but it's like the nuts and bolts of stuff that you're going to be needing to use in order to access some of the other things that we're going to be doing. And namely, this is stuff to do with powers, indices and surds. It's what for the last few years now we've been doing with our A-level maths groups, and it gets you payback in year 13 when we're able to spend more time revising for the important things of the A-levels, of the exams. And so the videos that I'd like you to watch and the questions that you do have all been prepared by Mr. Cooper, because he was doing the previous year. And I would like to have a go at those. I was going to redo them myself, but having watched them, I thought, oh, they're really quite good. So I thought I'd leave them the way that they were, but I am going to add on a little bit of my own, just in case any of you were still wondering, why do we have fractional indices? And why do we have negative indices? What's the point? Where do they come from? So I'm going to do a bit of that now. And when you've done the work that's added on, it would be really great if you could email it to me, just so that I can check that we are all in the right place and ready to go in September. Okay, great. Well, here we go. So the question I just want to answer for you now is, why do fractional and negative indices exist? Well, I think in some ways the negatives are the easiest ones to demonstrate. We're all okay with the idea that if I take any number, maybe it was 3 squared, and I multiplied that by 3 to the power 3, that's going to give us 3 to the power of 2 plus 3, which is 3 to the power 5. Now, if we reverse the process and we divide, we take the powers. If the power you're dividing by is bigger than the other one, because 2 take 3 is minus 1, we would get 3 to the power negative 1. Now, if I was to look at these numbers and think about what they were, it's actually 9 divided by, which I'd write as a fraction, 3 to the power 3 is 27. And if I was to simplify that, I would get 1/3. I could have written it as 3 times 3 over 3 times 3 times 3. And I could cancel that, divide top and bottom by 1 by 3, divide top and bottom by 3, and that would have left me with 1/3 that way. Now, if I had had 3 to the power of 4, say, that would have given me 2 take 4 is negative 2. That would have given me 81 under there, wouldn't it? And if I did that, that would actually be 1/9. And I could have put that in here by putting in one more times by 3 in there, and 3 times 3 is 9. But that we could also think of as being 1 over 3 squared. So this is why we get the rule that when you've got a negative power, you use the reciprocal, that is the fraction turned upside down. I know that 3 is not a fraction, but we can think of any whole number as 3 divided by 1, by that whole number divided by 1. That's what we're talking about with the reciprocal. And the same thing happens if it's a fraction to a power. We turn the whole thing upside down and turn the power positive. That's why that happens. And how's about the fractional side of things? Well, that's going to make us think about surds. You may be aware from your thing, if I had 2 squared and I multiplied it by 3 squared, well, 2 squared, that is 4. 3 squared, that is 9. We all know 4 times 9 is 36. But we could also do it in this other kind of a way. We could say that it's 2 times 3 all squared, because the numbers are multiplied. 2 times 3 is 6 squared, and that always works, and it goes in reverse when we have the surd situation. But if we just take this idea of a square number, 3 times 3 is equal to 9. 3 to the power 1 times 3 to the power 1 is equal to 3 squared. Yes, we know that. What about, what else can we think of as 3 as being? Well, it's the square root of 9. If I had the square root of 9 times the square root of 9, well, that's 3 times 3. That gives us 9. But what is our rule when we multiply powers? It's that we add the indices. So if I had 9 to the power of something times 9 to the power of the same thing, and getting it to 1, those two numbers, the question mark, must both be the number that if you add it to itself, you get 1. So that would be a half. So this is why the half is a square root. Now, if we were to have a power of 3, then that can come down and we can get thirds as well. If I had 8, for example, is the cube root of 8 times the cube root of 8 times the cube root of 8. Well, we know the cube root of 8 is 2, but we can also think of it as 8 to the third times 8 to the third times 8 to the third. And then we get 8 to the 3 over 3, which is 8 to the power 1. And it continues to work on when we've got more interesting fractions that don't just have a 1 on the top. Now, I hope that helps you make a little bit more sense of what's going on with all the other stuff that Mr. Cooper is going to take you through on the following videos. Once again, I look forward to seeing you in September. Have a lovely summer. Cheerio.